Thanks very much. We're in the home stretch. So Wednesday, we talked about quantizing compact semi-simple Lie groups. And we ended up with this formula here, which, though it's just one result, it encapsulates a great deal of the representation theory of these compact semi-simple quantum groups. So I wrote down this formula. I forgot to write down the actual formula for the isomorphism. So how you take a function, an L2 function on KQ, and turn it into a field of Hilbert-Schmidt operators. So let's just recap that. I mean, I more or less said everything orally, but I just want to make sure we're all on the same page here. So we're looking at SUQ2. We take a pair of functions f and g on SUQ2, and we take their L2 inner products using this Plancherel integral that we defined. And the claim is that this inner product can be calculated by decomposing this L2KQ representation equipped with the left and right regular representations of our quantum group into a family of finite dimensional left and right representations of our quantum group, namely the matrices over every one of the irreducible representation spaces. So matrices, of course, left and right representations just by acting on the left by precomposing, postcomposing, and acting on the right by precomposing with the representation. And we get exactly the Hilbert-Schmidt inner product of f and g, which I'm now interpreting as polynomial densities instead of polynomial functions, so that I can represent them by convolution on these representation spaces. I take the Hilbert-Schmidt inner product, but twisted by this operator q to the power of h, which is some diagonal, positive diagonal matrix. And the philosophy here is that you should see this family of functionals, so indexed by m, the highest weight of our irreducible representations, and given by on the mth endomorphism, the mth matrix algebra, I'll act by 1 over the quantum dimension times the twisted trace, the quantum trace, if you like, of the endomorphisms. This should be considered as some kind of non-commutative counting measure on the space of half integers. So now each half integer is not given by just a one-dimensional copy of C, it's given by a finite dimensional matrix algebra. The twisted trace renormalized is a linear functional on that. You can see that as a counting measure in some non-commutative sense, and that is precisely the Plancherel measure. So even for the classical groups, without doing quantum stuff, you could consider now the q to the h is just the identity, so it's just the trace, but you can consider this family of traces as being a non-commutative Plancherel measure on the dual space, the unitary dual of a compact group. And we've got exactly the same thing here, except we have these positive operators inserting themselves into the formula. In the world of representation theory, these are called Duflo-Moore operators. And in the classical world, they only occur when your group is not unimodular, which cannot be the case for a compact group, for instance. So you'll never see this unless you go to, say, the AX plus B group or something like that, where you'll start having Duflo-Moore operators appearing in your Hilbert-Schmidt inner products. But here it happens even for finite dimensional groups. Okay, so that was all yesterday. Today, we want to go to the non-compact case. And it's exactly the same philosophy. So I'll start with the classical world. So this is SL2C. If I'm not mistaken, this was Harish-Chandra. So Gelfand and Neymark proved this for SL2R, the analog. And the SL2K, C, I believe, was Gelfand and Neymark and Harish-Chandra more or less at the same time working on the same thing, but it was really Harish-Chandra who put it into the general context for all first complex semi-simple Lie groups, which is the easy case, then real semi-simple Lie groups. And you get the following thing. You get, again, L2 functions on G, equipped with the left and right regular representations, decomposed, now not as a direct sum, but a direct integral of Hilbert-Schmidt operators on a family of irreducible unitary representations of our group, which I've called here L2 of E mu lambda. And let me say what those are. well, let me not specify. We'll get to what they are shortly. Let me just say that they are some family of unitary irreducible representations for SL2C called the principal series representations. They're actually representations on some line bundles over the flag variety. And they are indexed by two parameters now, a discrete parameter mu, which is a half integer, and a continuous parameter lambda, which is a real number. Yeah. You should think of lambda as being in A star. So yeah, actually more correctly in I times A star. But they correspond to representations of, so characters of the upper triangular subgroup, and the upper triangle, so the AN subgroup in G equals Kn in the Iwasawa decomposition. And as such, yeah, characters of the AN subgroup are given by elements of A star. So you should think of it as A star. I call it IA star because we want unitary characters, but it's really IA star and not T star that we're looking at here. You need to make a technical remark now because we're dealing with infinite dimensional representations. For any F, let's say, compactly supported, continuous would be enough. The representation, so the integrated representation of this function on my infinite dimensional representations is always a Hilbert-Schmidt operator, which is convenient because it means that the following formula makes sense. I can take the Hilbert-Schmidt norm of all of these family of representations indexed by mu and lambda and integrate them over half Z cross R, or if you like, the weight lattice cross IA star, if you know what that means. Modular, so with respect to this measure, which Harish-Chandra worked out, dm, where dm is this guy here, it's half the norm of mu plus I lambda squared times d lambda, the Lebesgue measure on R, times d mu, the counting measure on half Z. So it's an extremely elegant, rather simple formula, considering all the technical details that you need to get there. It comes out being rather pleasant, and it's entirely analogous to the Peter Weil formula that we had on the previous slide. Okay, so that's the classical case from early last century. Yeah. So these are, so in terms of, these are precisely those irreducible representations which are in the spectrum of the reduced C-star algebra. And that is almost a tautology because the reduced C-star algebra is defined by closing with respect to the representation on L2 of G. So those representations which appear on the right-hand side there must be precisely those that extend to the reduced C-star algebra. There are other representations other than these principal series ones, the complementary series, the trivial representation, which do not appear at all in this formula. And this is the difference between the reduced C-star algebra and the full C-star algebra for one of these non-compact groups. In the very last years of last century, 99, I think this was published, Wolfenmeyer and Roche figured out that you can do exactly the same thing for the quantum version of SL2C, which had just recently been invented by Podlosh and Romanovich. So that was early 90s that Podlosh and Romanovich invented their analytic version of the matrix group SL2C, using a construction that I'll describe shortly. And they found, so Wolfenmeyer and Roche were able to prove a formula which is almost entirely the same as Harish-Chandra's formula. So I've just put in red the things that change. We still have principal series representations. They're now indexed still by an element of R, if you like, but there's some periodicity in that. In the same way that we saw yesterday, there's some periodicities due to the fact that Q numbers have some periodicity because they involve Q to the power of something. The same appearance happens here. So we replace the continuous parameter lambda in R with the continuous parameter lambda in R modulo 2 pi of the log of Q times Z. So a circle now. Of course, as Q goes to 1, in the limit log Q will go to 0. So this lattice will get wider, sparser and sparser. And in the q equals 1 limit, we'll get back to the real number. Our circles will get bigger and bigger and become a real line. So there is some coherence in this formula. The other thing is that in the Plancherel measure, the coefficient is no longer a standard number, it's a Q number, but that's almost to be expected by now. We've already seen that this is what happened in the compact case, and exactly the same phenomenon happens here. And the Duflo-Moore operator also appears. Just for convention reasons, it comes out as Q to the minus H. I think there would be other ways of organizing a convention so it was the same Q to the power of H, but it's roughly the same thing as this operator K being represented on each one of these infinite dimensional representations, which gives you your twisted or quantum Hilbert-Schmidt norms, and you find exactly the same formula as Harish-Chandra found. So it's a very appealing situation. But now I need to tell you what this formula means, because I haven't told you what any of these representations are, or even what the quantum group is. So now we're going to go down to the blackboard, unless there are any questions at this moment, and explain the ingredients of this formula. And then if we have time at the end, I'll give a very, very quick run through of how you might prove this formula. So any questions? Maybe before we get started, let me point out how hard this was and remains to be. We know now how to, thanks to Podlish and Aronovich and people who came after them, and Drinfeld, who preempted this somewhat on the algebraic side, we know how to quantize all the complex semi-simple Lie groups. So everything I'm going to say in this lecture will generalize as long as we only consider the complex groups. If you want to know about what happens in the real groups, we still don't really know. So the world hub of this at the moment is Kenny and his cohorts at Brussels, where they are trying to uncover what the correct way to quantize the real semi-simple groups, Lie groups, is in this world of unitary representations and C-star algebras. But it remains an open problem and a surprisingly difficult one to figure out what's going on there. So let's stick to the quantum world. And the starting point is the Iwasawa decomposition. This guy here. So the notation is, well, let me keep my life simple by just taking SL2C, but of course this could be any complex semi-simple. K is its maximal compact. AN is going to be the upper triangular matrices in SL2C with A being positive. So it's again a three-dimensional Lie group, 1 dimension for A, 2 dimensions for the complex parameter N. And it turns out that this guy and this guy, so that's three-dimensional, that's three-dimensional, these are actually Poisson-Lie duals. I'm not going to tell you what that means. I'm going to let your imagination wander if you get bored later in the talk and imagine what Poisson duality might mean. It's not necessary to understand that for this talk, but it's sort of good philosophy. Okay, the other group that I'm going to need is the diagonal subgroup T, compact diagonal subgroup T, which is just a circle. Okay, and what does this bow tie here mean? This bow tie means that as a manifold, G is isomorphic to K times AN by just using the multiplication rule, either by taking K times AN or by taking AN times K. But neither group is normal, so it's not a semi-direct product. It's a double product in some sense. Nonetheless, because I can write everything uniquely as KAN or ANK, I'm going to get exchange relations. So if I have written something in the wrong order, I'm always going to put my A and N together. So if I've got AN times K in the wrong order, I can rewrite it as K times AN with some new K prime and AN prime in some way, given some rule that I could work out if I had enough time and enough coffee. But for the moment, I don't care. Just there is some exchange relation. So now we want to quantize this. And the philosophy is that Poisson dual, when you quantize, becomes Pontryagin dual. This is just philosophy. Well, it's more than philosophy, but for me, for this talk, it's just philosophy. And it justifies the following definition, which you could make without any philosophy, but it would be difficult to understand why you would want to do it. So still, Q for me is going to be in 0 infinity. I don't want it to be 1, otherwise I'll get something else. I'm going to define dGQ, the convolution algebra of distributions, polynomial densities, if you like, smooth distributions on GQ, to be dKQ across ANQ. But ANQ I'm going to replace by the Pontryagin dual KQ hat. And the Pontryagin dual, as we saw at the start of yesterday's lecture, is just a way of renaming the function algebra as the convolution algebra and vice versa. So it's as a vector space, it's this tensor product here, algebraic direct tensor product. But the rules that I want to apply to this are not just the tensor product multiplication, because I expect to have exchange relations. Yeah, so for me, OKQ is matrix. It's the matrix coefficients, and DKQ is the finite dual, just the direct sum of the matrix algebras. Nothing more complicated than that. And here, the multiplication is just pointwise multiplication. So it's a discrete quantum group, if you like. It's just a direct sum of matrix algebras. It's represented on every one of these irreducible representations for Km just by letting that component act on Vm. So it's a very simple object, but it also has, the interesting thing is it also has a coproduct. So it is a quantum group as well. Sorry? Yeah, minus analysis is UQG. It's the finite version of UQG. It's the bounded version of UQG. It wants to be UQG. And in fact, I could do this whole thing with UQG here instead and UQKC here. And I'll get also a good definition of the universal enveloping algebra of this complexified semisimple liquid. The exchange relations that I want are what happens if I have something here which is multiplied in the wrong order. That means what if I have something of this form here? So it'll be maybe 1 tensor x times f tensor 1. So I'm going to use this bow tie for the tensor product when I'm seeing it as being in this double product here. And the rule is, it's very elegant. I mean, I have a way of pairing x and f here. These are just dual objects in this quantized world. I'm just dealing with actual dual objects. So I could just pair these. So what I'm going to do is take a bunch of coproducts. yeah, x2, f2. And I'm going to multiply it by a bunch of scalars, which are given by the pairing. So x1, f1 is a scalar, complex number. And also, I'm going to put my other scalar at the other end, even though logically it would go at the front, I guess. That's just another scalar, but it looks prettier if I put it at the end. Okay, and of course, this is a sum because these x1, x2, x3 are just stand-in variables for some finite sum of elementary tensor products given by the double co-multiplication, etc. Yeah. Well, what? So that would be if I were dealing with the function algebra and not the convolution algebra. So here I'm on the convolution side. And remember, multiplication in the algebra corresponds to multiplication in the group when I'm working on the convolution side. Right. And it's in the group that I have exchange relations. On the topological side, this is just a diffeomorphism, just a direct Cartesian product of manifolds. So you're absolutely right that I want my diagonal embedding to be just a standard diagonal embedding. Because I'm not messing up the topology here. I'm only messing up the group laws for exchanging these two. So this says that I have a non-commutative group law between these two components, but I want a co-commutative topological law, which means I want the standard coproduct on this tensor product. Namely, if I take the coproduct of x bow tie f, I should get x1 bow tie f1 tensor product with x2 bow tie f2. So this is the convolution. Yeah, question. Is it where? Sorry. Yeah, that's x2 f2. Yeah. Oh, it's just my writing is not very clear. Okay, so I'm not twisting the diagonal embedding, I am twisting the group law. As mentioned, we could also do this. This is not what Woronovich did. This is called the Drinfeld double. And it's not what Woronovich did, but it's dual to what Woronovich did. No, I want x2, f2 because, oh yeah, I've done something wrong. Yeah, you're right. Yeah, thank you. Yeah, no, hang on. I think I've actually got things wrong here. No, it's here that I've got things wrong. F and X. Spend some time making sure this is right. Does that look better? Thank you. Okay. Good. So what Woronovich did was the same thing with OGQ instead of DGQ. He defined OGQ to be OKQ tensor DKQ with the standard multiplication, just element-wise multiplication, and the coproduct, which is twisted. And to twist the coproduct, what you need to use is the multiplicative unitary, and I won't explain that. But it's an entirely analogous but dual picture to what I'm describing here. Good. So now we've got a group. And I'm claiming to you that this group deserves, or the quantum group deserves to be called the quantization of SL2C. Okay, let's just believe that. What we now want to do is study the representations, and it's really once you start to see the representations that you start to believe that this really is a quantization of SL2C. But maybe it's worth just taking a second to appreciate how magical this is. You just take an object which you've studied and its Poincare dual, and you smash them together using their natural pairing, and you get something incredibly beautiful which mirrors something that doesn't look at all alike in the world of classical groups. It's really a truly marvelous construction, in my opinion, one of the highlights. Yeah, so I could have started with any semisimple compact semisimple Lie group and done exactly the same procedure, and I'd achieve exactly the same result. A representation of this convolution algebra, which should be thought of as a representation of a group, or a co-representation of the functions if you want, but let's stick with representations. On a Hilbert space H, it's going to be given by two things. It needs to be a representation of the first part, the compact group, and a representation of the function algebra. That's something we haven't talked about at all yet on the Hilbert space, on the same Hilbert space. And those two representations need to satisfy this exchange relation. So I'll say with compatibility, this compatibility is also famous. It's called, suitably interpreted, the Jette-Drinfeld condition. And indeed, if you dualize the representation of the compact part dkq to get a co-representation of okq, you will precisely get a Jette-Drinfeld module. I'm not going to write down what the compatibility condition is. You could interpret it from that. Let's do the example. So the principal series representation of parameter mu lambda in half Z cross R, maybe IR is better, but let's not split hairs, is as follows. So I need a Hilbert space, H mu lambda, and it's going to be a closure of some algebraic vector space, just a countable dimensional vector space, which I now need to describe. And now we're getting into Jan's territory. This should be thought of as an induced sections of induced vector bundle, an induced line bundle over the flag variety. So what do I mean by that? So it should be sections of an induced bundle, as Jan's been telling us about. Again, you don't need to do details here. I'll tell you exactly what it is in the final thing, but I'm trying to motivate it geometrically. So as has been repeated several times, this should be functions on the group. I'm not allowed to write that. The group doesn't exist. It's just an algebra of functions, but it's functions on the group such that normally in the classical case, it would be fkt is fk times some character of t, and I'll write t as e to the t ih. where H is our diagonal 1 minus 1 matrix. And this should be e to the I2 mu t times fk. That's for all k and k, and t a real number. That's the equivariance condition, which gives me this line bundle, sections of this line bundle. I now want to differentiate that because I'm not allowed to talk about group elements, but I am allowed to talk about enveloping algebra elements. So differentiating this at t equals 0 gives me the action of H by right regular representation. We've talked about that already. So I can say more correctly, this is elements of OKQ, functions on KQ, such that if I hit it with H, I get 2 mu times F. If you want, this is precisely the mu weight space for the right regular representation. Good way of looking at it. So this line here doesn't really exist, but the rest is totally fine. Because it sits inside O of KQ, I can take its L2 completion to get an L2 space of sections, and that's my Hilbert space. Now I need to tell you what the representations are. Clearly haven't got this technique mastered. Sorry? Oh, yeah. Yeah, lambda is gone. Thank you. Lambda is gone. Why is lambda gone? Seems unfair. In fact, the Hilbert space on which these representations act is independent of the continuous parameter lambda. Depends only on the discrete parameter. So the Hilbert spaces are independent of lambda, but the representation will depend on lambda, as we'll see shortly. This is the same thing that happens in the classical world. Principal series Hilbert spaces depend only on the discrete parameter, but the representation depends on both. The compact part is easy to make act because this sits inside L2 of KQ, and I cut it down by the right regular representation. I'm allowed to act by the left regular representation. It's invariant. So that means X acting on F is given by, to make it, well, let me do it like this. Yeah, actually, let me do it like this. Pi mu lambda X acting on F is given by the right action of Sx. As usual, we have this fundamental confusion that left translation gives a right representation and right translation gives a left representation. So this is indeed a right representation, and I'm using the inverse to convert that into a left representation. So it's a standard thing. Again, it does not depend on lambda. And then I need a representation of the function algebra. And this is beautiful too. I'm going to use twisted adjoint. As follows. So adjoint would be if I were to do A1 F S A2. Take the coproduct and make it act on one side and the other in the left way. I'm going to use A3 here and use the A2 to give this character twist, which is q to the power of lambda. I'm going to actually use lambda plus 1. You could use lambda. I wouldn't be unhappy about that, but it's going to be better if I use lambda plus 1 to the power of h. So this is one of these diagonal matrices appearing again. I use this to twist my coproduct and then make that coproduct act by conjugation on my functions. The magical formula looks very nice. You can check that it satisfies the Jette-Drinfeld condition, so I get a representation out of it. Seems a bit unmotivated. If you want to motivate it, you can look at the parabolic induction. So rather than inducing over T to K, you can induce over BQ to GQ, since K over T is equal to G over B. Geometrically, these are the same things, but I see the full structure of the representation in the G mod B model because G acts rather than K. I then need to restrict that action to K instead of functions on G, and you'll find you get exactly this formula. Okay, more than that I will not say just because of lack of time, but you can, this formula does come naturally from a notion of parabolic induction in this world as well. Proposition about these guys. Many facts. So firstly, this is Jette-Drinfeld compatible. So I get pi mu lambda is a representation of dgq. The second thing is that it acts boundedly. So extends boundedly to the L2 completion, so that I get not necessarily a unitary representation here, but a bounded representation in which the compact part will act unitarily. So this is sometimes called an admissible representation. The third is that, what did I want to say for the third? Oh yeah, this is unitary if and only if. Oh yeah, I did more than I needed to here. I could have taken, instead of a parameter, a real parameter there, I could have taken a complex parameter and everything would still work. But it's going to be unitary if and only if lambda is in IR. So that some of these representations are just admissible representations, but if I'm on the imaginary axis, or in fact imaginary circle because of the periodicity that I've talked about, I'll get a bunch of unitary representations, and these are the unitary principal series. This is not to say that the others aren't unitarizable. There are some of them that are unitarizable, and that's where you get the complementary series, for instance. But in general, they're not even unitarizable. Fourth thing, maybe just mention quickly, I don't think I'll need to use it, but that H nu lambda is isomorphic to H minus mu minus lambda for all. Oh, no, that's not right. Drat. I need one more line before I can do that. That's my Spanish. I want to mention irreducibility. And looks like a little bit of an ugly condition here. The short answer is generically it's irreducible. But there are a few specific points in this parameter space where it has some reducibilities. And it's precisely when plus or minus the discrete parameter aligns with the absolute value, sorry, plus or minus the continuous parameter aligns with the absolute value of the discrete parameter plus some positive integer, strictly positive integer. Should be n positive. And then there's this periodicity in the imaginary direction, which is always hanging around. Let's not worry about that. But in particular, the unitary ones are always irreducible. So the unitary principal series are all irreducible. So that in the Harris-Chandra formula, Plancherel formula that I showed on the slides before, the ones that appear are actually all irreducible. Maybe I'll stop there. There are other things I could say about this, but it's probably best to just stick with that. Okay, so with all of that, the Plancherel formula that I showed you at the start now makes sense. The only thing that remains to do in the remaining 7 minutes is to prove the bastard. That is the only place it comes in. And the reason why I've used lambda plus 1, I forgot to mention that, is precisely so that unitary sits on the axis. Otherwise, there'd be a shift. And this plus 1 is actually rho, the half sum of the positive, it's 2 rho, the half sum of the positive weights. No, sorry, it's rho, the half sum of the positive weights with my parameterization. Thank you. I had to change one or the other. Thanks, Pablo. So the other thing that I was going to write up, but which I don't think I'll bother, is that these guys, when they're irreducible, I have h mu lambda isomorphic to h minus mu minus lambda, which, if you know anything about semisimple groups, looks like a Weyl group action, and indeed it is. So the Weyl group action on the parameter space results in isomorphic irreducible representations. If they're reducible, I'll still get isomorphic irreducible components, irreducible factors in the Jordan decomposition, but it's just they'll be organized in different ways. One will be split one way and one will be split the other way. So they're more or less isomorphic in general. But I don't think we need that, so let's ignore it. Let's get back to Plancherel. So what we're supposed to prove is that this guy here, so I haven't told you what the Haar integral is on GQ. Turns out to be easy. It's just the product of the Haar measure on KQ and the product and the Haar measure on KQ hat. So, okay, again, I won't write it down, but it's very easy Haar integral on this guy. And I need to prove that this is an integral over the parameters mu and lambda of the twisted trace of the q to the minus h, this guy here, represented in this irreducible unitary principal series representation with respect to this proposed Plancherel measure. A remark, so let me just replace this guy by a single distribution. If I calculate this by the magic of Fourier transform, the magic of Fourier transform, the philosophy is that the integral of a function is the same as taking the Fourier transform and evaluating at 0. The same is true here. You evaluate the Fourier transform of this guy at the identity that's given by the co-unit. Okay, so this is a fact about the Haar measure. It's given by precisely the dual of the co-unit on the dual space. And by replacing that, I just need to prove, I need to calculate E hat U, which is hopefully the integral over this parameter space of this twisted trace of the representation of this guy U times Q to the minus H dmq mu lambda. That is our goal. There now ensues a long but not particularly difficult calculation once you line everything up, which you can do just in the case where U is a product of a matrix coefficient in DKQ and a matrix element in OKQ. Sorry, I did that the wrong way around. A matrix coefficient in OKQ and a matrix element in DKQ. You can do this calculation. You find a lot of miraculous cancellation because you're integrating over a circle. Lots of Fourier coefficients just magically die. And I'll tell you what you get at the end. You get a sum of two terms. One is a trace of pi 0, 1, if I'm not mistaken. No, I think it's minus 1, 0 of some U tilde minus a trace at pi of 1, 0, minus 1, 0, no, 0, minus 1. I think I've got that right. Some U tilde where U tilde, I can never remember what it is. It's something vaguely related to U. It's something like you take the co-unit in GQ of 1/10 of the co-unit in KQ hat of U or something like that. Big question mark, big question mark. It's not very important. There's some manipulation you have to do to your U to arrive at the appropriate U tilde to put in here. The moral of the short story version of the story is when you do this integral, you calculate all the things that vanish automatically. You're left with a difference of two traces in principal series representations. Surprisingly, not unitary principal series representations anymore. I'll mention that in a second. One of them has non-imaginary parameter in lambda, but you get this difference of traces. So what remains to do is just to calculate that this difference of traces is exactly the co-unit. And you can do that in the case of rank 1, so for SL2C, you can do that just by brute force. But if you want to understand what's really going on, you need some more technology, which unfortunately, very sadly, I don't have time to do. But maybe I can just show one or two slides quickly, and then we'll finish up with that. Because the reason I wanted to show it is because it comes back to BGG complex. So magically, it ends up in the world of geometry again. So in fact, this representation here, as I said, is acting on a line bundle. It's precisely the trivial line bundle over the flag variety. This guy here is the 0, 1 forms over the flag variety. The flag variety here is CPQ. So we're talking about the Podler sphere. And we have exactly the difference of the action on 0, 0 forms and 0, 1 forms. And as we all know, there's a Dolbeau operator which acts between these, which is almost an isomorphism. It has trivial co-kernel, and the kernel is just the constant functions. We get precisely the co-unit, evaluating on the constant function. So it's kind of a magical thing, and it suggests that something more general should be going on. And let me just skip all the algebra, which is due to, let me mention Joseph and Lester, because they're the ones that did all the hard work here in converting the algebraic BGG complex in terms of Verma modules into a geometric BGG complex in terms of unitary principal series in terms of principal series representations. Although they didn't phrase it in these geometric terms, that's exactly what they were doing. The key point is this guy here. Where is it? There. That there's an equivalence of categories between category O or some category of category O where all the weights lie in some particular lattice, and what I call, or what are called, Harish-Chandra bimodules, which are some alternative interpretation of DGQ representations, which I wanted to talk about, but I ran too long. And this equivalence of categories sends a pair of Verma modules, their ML and MR, to a principal series representation. So this tells you basically if you have a resolution or an exact sequence in Verma modules, you can convert that into a resolution or an exact sequence in terms of principal series representations. Or if you like, geometric differential operators between line bundles over the flag variety. And what you get is precisely the geometric BGG resolution from the algebraic BGG resolution in terms of Verma modules. And it's well known that this geometric BGG, these BGG resolutions have trivial, I mean, it's called a resolution precisely because it has trivial cohomology, so that the index of this guy will be precisely the constant functions on the left-hand side. And by using the Lefschetz trace formula, you'll see that the difference of these traces here must be precisely the trace on C, the trivial representation, and the trivial representation is the co-unit, and you can deduce the Plancherel formula from that. So that was extremely fast at the end, but I just wanted to give you a flavor that hiding in all this algebra of the Plancherel formula, there is beautiful geometry as well, coming from precisely the kinds of things that Jan was telling us about in the previous hour. Thanks very much.
We've gone to the last slide. This is called fusion form on channel scale.
Yep.
It's quite a job to construct these bundles as proper image. You probably have a job about context, etc. The appropriate fusion. Is that really all in their paper?
No, it's not in their paper. So, I mean, like I said, they don't describe it really in terms of geometry. They describe it in terms of Harish-Chandra bimodules. So it's all done completely algebraically. And yeah, so that's this. I mean, I've stated as a theorem of Joseph and Lester. They do interpret it as a Drinfeld, a module over the Drinfeld double. So they're basically there. You actually don't need any differential calculus here.
There's a lot more underlying structure.
There is, which I'm, to be honest, doing my best to avoid because it's hard. Differential calculi, as we know, are not easy to construct. Yeah, so this gets very close to stuff due to Heckenberger and Kolb, as you know. So yeah, this point of view is very different from the sort of Heckenberger-Kolb style point of view, or the Voronowicz differential calculi, or the work that you and Edwin have done. It's a very different point of view because it's really coming from pure algebra and trying to do as little geometry as possible. Basically because algebra is, let's not tell anyone outside this room, algebra is easier than analysis. I don't mean that in a facetious way at all. The fact that algebra is easier means that with algebra, you can go further with the same amount of effort. So the algebra involved in this Joseph Lester stuff is extremely difficult. There's a lot of hard work to get through, but because it's algebra and there's no analysis, you can somehow push further with less effort. Yeah, please. Yeah.
In the analytic setting, you can get rid of the double cross product and make it into a semi-direct product by changing OQ, OQ, So yeah, you can replace the, well, not this one, but the way you described it in your previous talk, double cross product of EQ and let's say DQ and OQ.
Yep.
And you can replace the OQ by a graded version of a different product. But it's and then it becomes a semi-direct product. but it's still isomorphic. And I mentioned that depending on the model sphere, like I mentioned, the model sphere, and I think that you trace one inside the radio pressure.
Okay.
And so that might fit, I don't know if it's up, but it might fit quite well.
Except the comment, yeah, you'll have to tell me about that afterwards because I don't know anything about that. Yeah, you're right. I should absolutely have said that your work and work of some other people, there are instances where we can explicitly calculate the BGG complex coming directly from geometry, just knowing about the structure of differential operators on the flag varieties and their relations. Yeah, you can, yeah, as you know very well, you can absolutely compute this using geometry directly. But sure. Yeah, well, I don't know whether there's an analog of Joseph and Lester's equivalence of categories when you're outside the world of. This must be known in the classical case. I'm not expert enough to tell you what the answer is, but yeah, you can create geometric BGG complexes, as we know from algebraic BGG complexes over partial flag varieties, or for non-minimal parabolics. I presume you can do the same thing in the quantum world, but yeah, that definitely remains to be done, and that it's sort of. Sorry, I didn't hear. Totally believe you. Yeah, I don't know enough about that to have a comment. All right.
Speaker for a series of lecture.